Hello, everybody. So I received a request to kind of redo the calculation quickly for the independent sample t-test because there were, well, we did run into this issue while calculating it, that I did the aliquots wrongly on the, what was it? That's really wrongly, degrees of freedom, I believe. Okay, so let's do this again. I quickly walk you through the calculations. And so again, so this is the in-class spreadsheet that we have seen. It's straightforward. We're just gonna quickly transpose this data. And transposing is always, so you right click on the cell where you want the data to go. You go on what is called here paste special. And you select transpose and it basically will get it from a wide format to a long format. Then essentially it's business as usual. We're calculating the averages. We're calculating the averages, and I'm gonna make sure that here the average also includes the last number because it's a little longer than the other selections. So again, it's the wine drinkers. So we have those that were served the $10 bottle of wine as opposed to those that were served a $90 bottle of wine, purportedly $90. And we see significantly, we don't know yet whether it's significant, but we see higher ratings in average. So essentially, first thing we need to do, as always, we're going to do the deviation to the x minus x bar. That is essentially this minus dollar this. Okay, so we're gonna do dollar L $9 gets us this. This is not a difference, so now we can propagate this all the way down. Now essentially we're just bringing it here over to our second column. We need to change not only L to Q, but that essentially we're changing now the average calculation to the one of the $90 wine. We get now our deviations calculated. Now, second thing is x minus x bar, and we're squaring our deviations. Just square. So now we get the square of our deviations. We can copy this over here. The sum of squares is now essentially our pathway to get to our variance. And as said, because we need to pool the variance, we need to get to a pooled variance. For this very reason, we are only working with the variance at this point in time, not yet the standard deviation. So we are now dividing this by count of all these entries. We need to close the bracket here. So count is a separate function that needs to go in a bracket because we're doing count minus 1. And here we're getting to 0.64. If we're doing the same function now here, we're essentially taking this sum of squares, we're dividing it by bracket open count S3 to S8. So this minus 1. This will get us to our variance. So we have here an SS square X, and we have a variance X, correct? So this means that there's a sum of square for population 1, population X, population 1, and an SSY for population Y or 2. Now we have the same here for the Y. We do variance X over variance Y. And now what seemed to have been the issue is this DF ratio. So when you have a proportion of, so you have a whole, the whole sample population here for both groups is essentially 1, 2, 3, 4, and 5 is 9. The degrees of freedom, we're subtracting 1 for each group. So we're subtracting each entry that can be removed from a variable and still allows for the calculation of the sum of squares. So when we only had 1, 2, 3, no, we have, okay, let's say the following. Let's say this, and this, and we only have the sum of squares of 1.94 given. We can calculate this one just knowing the degrees of freedom, which is here 1, 2, 3, and the sum of squares, correct? So if we have now the sum of squares given, and we know the degrees of freedom, we can calculate this as a missing value. So we would need to do equals now this multiplied by 3 minus this, and this. This would essentially get us now, not to where I thought it would go us. It's of course not the sum of squares, because then I don't need to multiply by 3 because that's the variance. So essentially, so we can calculate this later, this missing value by knowing the sum of squares and all the other entries except for 1. So 1 we can drop, and we can do this for both groups, and this will allow us to determine the degrees of freedom. And the degrees of freedom is essentially what will be used for T distributions. Good. So I hope this made the degrees of freedom a little clearer. So we have degrees of freedom here with degrees of freedom total, DF total is here. The count of these entries plus the count of these entries. This gets us to this overall count. And this now minus 2 because it's 2 groups. So this gets us to the 7, right? So now count of these minus 1 and now we're calculating the proportion, right? So we have 7 as the 100% divided by the 100%, which is now this, gets us to 0.43, which is not correct because I didn't subtract here. No, it's correct. It's count L3 to L6 minus 1 divided by, okay. So essentially this is 0.43, and this is our proportion. So now we're doing the same thing with count Q3 to Q6 Q7, because it contains more entries, divided by the total, which is not R12, but it's, oh no, it is R12. Yeah. So now we need to also adjust this. This is now Q. And Q3 to Q6, now it's a Q7. And count of L3 to L7, L6. Don't need L7. That's again the 7. And this is 0.57. These are the ratios. The ratios essentially that we have for the degrees of freedom as part of the overall complete group, which is here our 9 entries. This would be these and these entries. So this is 7, and the fraction of this is essentially 3/7 and 4/7. Good. So what we're doing now, we're just creating now a variance that is weighted according to the sample size, or the degrees of freedom, more accurately expressed. So this is now essentially the variance of X multiplied by this proportion. And that gets us a certain weight to this variance that essentially is a reflection of the degrees of freedom in the respective group. So if we're doing the same for variance X, so this is degrees of freedom X, this is degree of freedom X, this is degrees of freedom Y. So now we're aliquoting this variance. This is RS, this is supposed to be S10, S10. And now this variance is 0.57. This gives us a variance X, variance Y. And now we need to pull this together, right? And this is easily done essentially just by, so this is now the pooled variance. So now we're getting to the pooled variance. And the pooled variance is essentially the sum of this and this. Gets us to 0.84. These 0.84 allow us now to kind of more specifically get to the standard error of the mean squared. We're still squared. So this is an SEM X and SEM Y. But careful, it's still squared, right? So we're still on the squared line. So Norton and Heinzen, essentially, if you look here at the slide, they're labeling this different. This is probably always a part of where the confusion comes from. So they're labeling it here. This one is here. They're labeling it an S square pool. So that is a squared standard error of the mean for this X. So this is S squared X gets us to S squared pooled with the weight. So this is here where we're already getting to a standard error of the mean aspect. So now we're doing this multiplied by divided by the count, which is here 4. And this variance divided by 5 gets us now the SEM X and Y. But this is squared, notably. Okay. So this, adding this up now, this is Y. So adding this up now this where we're coming to an SEM pooled. This is now this step here. This is where we're getting now. this is our pooled standard error of the mean. This is not the sum of this and this. Good, but this is still squared. And now we're doing SEM. Now we're doing SEM. We're taking this. SQRT. We're taking this. And we're coming into the 0.62. And this is actually here our S difference. S difference. Northern Hansen. And this is essentially what we are using now to calculate the T. And the T is now this minus, and let's make it easier. Let's say it's an overestimation of the quality of the minus this minus this. And don't forget the brackets when doing these calculations. Divided by the standard error of the difference. And this is now our T of 2.43. And this is this step, right? So you always have after the minus, you have your null hypothesis. So essentially you are subtracting your actual observed data, mx minus my, which is our 4 minus 2.5. And you're subtracting your null hypothesis, which is mu x minus mu y, being 0. This is why it drops off here, divided by the standard difference, by this S difference, which is the standard of the mean, the pooled standard error of the mean. And this gets you to the T. Good. And now we're doing the same thing for the effect size. So the effect size is essentially calculated in the very same fashion, right? So we are going now to this calculation here. No, that's not the effect size. Yeah, standard error. So this is also the standard error of the mean that we will be using for calculating the difference. So if you do, let's do this quick. Same story. So you do LLCI, 95% CI. You do this minus this multiplied by what was the degrees of freedom? Degrees of freedom must have been 2.36, I believe, 2.365 equals 2.365, 2.365. No, this is now lower limit minus 2.365 multiplied by your standard error of the mean. This is your S difference. So it gives us now 0.043. And for the upper limit, 95% CI, we're basically doing almost the same thing. We're doing this minus this in brackets plus, this time plus, because it's the upper bound of the 95% confidence interval, 2.365 multiplied 2.365 multiplied by standard error of the mean, 2.96. So 95% confidence interval is 0.0443 to 2.96. And I'm showing again the way this needs to be expressed. So we have now mean at 95% CI. And I'm showing this because I think it's important that you know how to do that and that you know how to show these differences. Mean, so this is the mean delta, mean difference. So you would show this as the following. So I'm gonna do this with concatenate. Don't feel compelled to do that, but it's a very good function to know. So this is concatenate. You're doing a difference now, which is this minus this, comma, and with quotation marks you actually can in concatenate you can enter text. So we're doing a bracket. We're doing 95% CI. Now we're closing this. No, putting quotation marks, close. We're doing now round. Taking out the lower limit. We're rounding it to 1 digit. We're again putting quotation marks, we're saying 2 to indicate that it's an interval. Round, upper limit, 1. Oh, forgot something. We don't need to close the parentheses. Now we're doing with the last bracket, we're closing another concatenate. So, okay, we need more decimals, otherwise it doesn't show the 0.04. So, well, we have, always have the same number of decimals in your, and whatever you're expressing. Yeah. So this would need to be changed. So it should be 1.50 to 95% CI. But you see what I mean to show, right? So this is really how this should be expressed in a scientific paper or in any reports or in your graduate classes. Then please use this format and really show your data that way. So this is the difference with a lower limit of a CI to an upper limit of a CI. Good, and then we have last but not least, we have now the effect size. And not this, we wanna go here. So here, that's the effect size, that's our D. So here we're doing now mx minus my, the same formula as the standard, but this time we're gonna take the full standard deviation. How we're gonna do the full standard deviation? So we are essentially whenever we're calculating the effect size, we're calculating the same difference. We're doing now the 4 minus the 2.5. That's the difference again. But usually with the t-score calculation, so it's the same formula in a way than the t-score calculation, besides that we are now using the standard deviation and not the standard error of the mean. So we're using now this pooled variance that we've gotten. But variance to standard deviation is essentially we need to employ the square root. We're doing this hereby, and that gets us an effect size of 1.63. Does that all make sense? All right, I hope this was a good exercise to kind of clarify the questions that you had, and this spreadsheet should be consistent with the last one we had. We'll post it with the announcement, but it should be good. All right, good. Happy Thanksgiving. Hope this was helpful, and hope this helps you to continue your studies, and to also allow you to use the work on the examples of the homework. And I see you on Monday, and we will be discussing ANOVA. All right, bye-bye.